We'll now discuss divisibility and modular arithmetic. So if a and b are integers with a not equal to 0, we say that a divides b if there's an integer c such that b is equal to ac. And this right here, this vertical bar, is our notation that a divides b. So for example, 4 divides 12, since 12 divided by 4 is 3, which is an integer. 4 does not divide 13, since 13 divided by 4 is not an integer. Some properties. If a divides b and a divides c, then a divides their sum, b plus c. If a divides b, then a divides bc for all integers c, so it divides every multiple of b. If a divides b and b divides c, then a divides c, so we have this transitive property. And finally, if a divides b and a divides c, then we have that a divides mb plus nc for all integers m and n. So this is basically combining numbers 1 and 2. Our division algorithm, let a be an integer and d be a positive integer. There are unique integers, q and r, where 0 is less than or equal to r is less than d, such that a is equal to dq plus r. And so q is whenever you divide, it's your quotient. So if we do a divided by b, q is the quotient, and r is your remainder. We use the notation q is equal to a div d, and r is equal to a mod d. So div is the quotient, and mod is the remainder. For example, what are the quotient and remainder when I do 102 divided by 9? Well, I can see that 9 goes into 102 11 times with 3 left over. So 11 is 102 div 9, and 3 is 102 mod 9. What about negative 64 divided by 5? Well, my goal here is to find numbers q and r such that negative 64 is equal to 5q plus r, where r is less than or equal to r is greater than or equal to 0 and less than 5. This works when q is equal to negative 13 and r is equal to 1. So if you divide 64 by 5, you would actually get a quotient of 12. However, if I let q be equal to negative 12, then this term right here would be negative 60, and I would need r to be negative 4. However, this doesn't satisfy my condition. So I have to increase this, or rather decrease it, to negative 65 in order to make this r positive. So negative 13 is negative 64 div 5, and 1 is negative 64 mod 5. If a and b are integers and m is a positive integer, we say a is congruent to b modulo m if m divides a minus b. And we use this triple equal sign to denote this. And if a and b are integers, a is equal to b mod m if and only if a mod m is equal to b mod m. So this gives us two ways to determine if two numbers are equivalent. We can either subtract a minus b and see if m divides that, or we can see if they are the actual same value, if a mod m is equal to b mod m. For example, is 19 congruent to 7 modulo 6? Using the first method, 19 minus 7 is 12, which is divisible by 6. Using the other method, 19 mod 6, well, 6 goes into 19 3 times, with 1 left over. In addition, 6 goes into 7 once, with 1 left over. So these are congruent. Is 14 congruent to 5 modulo 6? Well, 14 minus 5 is 9, which is not divisible by 6. In addition, when I divide 14 by 6, I get 2 with a remainder of 2. However, 5 mod 6 is 5, and since 2 is not equal to 5, these are not equivalent. I can also do very basic arithmetic. So for 12 plus 17, we start by breaking this apart. 12 divided by 7 is 1 with a remainder of 5. 17 divided by 7 is 2 with a remainder of 3. So I have that 12 is 5 mod 7 and 17 is 3 mod 7. So now I can just add 5 plus 3. 5 plus 3 is 8 mod 7, and 8 divided by 7 is 1 with a remainder of 1. So we get 1 mod 7. We can also multiply. So I already know that 12 is equivalent to 5 mod 7, and we should say 19 is equivalent to 3 mod 7. So now I can just multiply 5 times 3, which is 15. And 15 mod 7, so 15 divided by 7 is 2 with a remainder of 1. So the product is 1.